Yeah, so as I pointed out, there's like one thing I really want to get to, and we have hardly any time left. And it's important because for the people who are going on to be doing 220, it's really essential because we've been looking at atoms and molecules and reactions, but we haven't really dealt with energy. And energy is essential to the whole thing. I mean, we sort of remember from classes we've taken in the past what an exothermic reaction is and what an endothermic reaction is. Maybe we don't. But it's really important in determining like which reactions take place. When do they take place? Under what conditions do they take place? This is all, really important stuff to know. And so I sort of wanted to introduce this just, right under the wire. And then so this afternoon, we're going to work on some of these problems together. And then on Thursday, we'll finish up the particular part of thermo that I wanted to introduce and go over anything else. And also this afternoon, we're going to go back to chapter 7 and look at redox. I guess AJ's group has done a lot of work on in recitations with redox reactions and balancing. And so I wanted to do the same thing for the other two groups. And so we'll work on that this afternoon. So any questions about what we're going to try and accomplish in our last week together?
Where can we find the study guide again?
For the lab exam too on Thursday? I'll get it to you right after class. I posted the wrong one. And if you're in AJ's group, you're going to be doing a review. He's in charge of sending you a study guide if he's promised to do that.
Are we going to have a study guide for the final? Or are we just going to use study guides 1 and 2?
Use those, and I will write one for the last chapters. So yeah, use the study guides for 1 and 2. Use those, and I will write another one for chapters 6, 7, and 9. What will be covered, and then if it's not on there, it won't be on the test. Okay.
Okay. Thank you.
Yeah, no problem. Yeah, I no, believe me, I understand. You got to get enough to worry about without worrying about if there's a whole bunch of stuff in the textbook or whatever else that you'll be responsible for, and then find out that it's not going to be on the test. I don't want you to worry about that sort of thing. Anyway, so as I mentioned, I really want to get to talking about energy before we finish up, because it's a super important topic. And I think that it sounds scary. Thermodynamics, thermochemistry, like yucks. I think it's basically the names that chemists choose for these things are basically designed to terrify students. They're not really as scary as we think. Really, what I want you to think about is that we know what reactants are. We know what products are. Reactants are things that go into a reaction and are changed in that reaction to make products. Well, energy can be thought of exactly the same way. Energy can either be a reactant and cause a reaction to go forward, or energy can actually be a product of a reaction and be released at the end. So energy that wasn't there, or it was there in one form at the beginning, is then transformed into a separate form and released at the end. So we'll think of it that way. So in other words, he said, trying to make a dramatic segue, thermo is just the study of energy and its transformations. And that's the key thing. Because we'll find out that really what energy is taking energy from bonds. And we've learned all about bonds. We know that you share electrons in a covalent bond or in an ionic bond, electrons are taken and they're held together by electrostatic forces. You have these bonds. Well, what we haven't really thought about is that there's energy in those bonds. That's where the energy in chemical reactions comes from, is either making those bonds or breaking those bonds. And so thermochemistry is just a branch of thermodynamics, which is just changes in energy, that just deals with chemical changes and physical changes. And so when energy goes from place to place, it goes from one place to another place. Like when you open up the refrigerator, what direction does heat go when you open up the refrigerator? Does it go from the refrigerator out, or does it go out from the surroundings into the refrigerator? Which way does it go?
Into the refrigerator?
That's right, into the refrigerator. Because really what we'll learn is that there's no such thing as cold. Like, yeah, there's no such thing as that. It's just a lack of heat. There's only heat. Either you have it or you don't. And so you're either taking it away or you're adding it. That's like the two things you can do with heat. And so there's only two ways that you can transfer energy from place to place. One is by adding or removing heat from it. And two is doing work on something or having that something do work against its surroundings. That's it. There's only two things. You can transfer energy from one place to another. Either you're adding or removing heat, or you're doing work or having work done on something else. The other thing that we'll learn about energy is that we need to know what it is we're measuring. Where are we doing these measurements? Like when we do a reaction, and let's say it releases heat. Well, what does it release heat to? Where is it coming from? We have to know what's something called the system. And what are the surroundings? Well, we'll learn the system is just that reaction itself and nothing else. And everything else around it, including the entire universe, is the surroundings. So basically, if I'm doing a reaction in a solution, the solution is the system. Everything else is the surroundings, including the container, the room that the container's in, you, me, the sky, everything else. When heat gets transferred, it gets transferred from that solution out into everything else and then is lost. And we need to measure that transfer of energy. So the internal energy, and we just use a capital E for energy, capital E, oops. It's just the sum of all the potential energy. Now, potential energy basically is referring to things like chemical energy, and kinetic energy is just movement. So if I have molecules moving around, and then, we didn't get to gas laws, but basically gases have energy just by the molecules just zipping around. And the faster they go, the more kinetic energy they have. Now, the total energy in the universe always stays the same. So if there's a change in one thing, it's reflected in the exact opposite change in the other. So if I lose energy in my system, the whole universe gains just that tiny amount of energy, so that the surroundings go up as my system goes down. If my system goes up, the universe must have gone down, or the surroundings must have gone down. But when I add everything together, I get zero. That's the way we could actually measure. We use this law to actually measure the energy that reactions release. Because when we put a reaction in like some water or something like that, and we measure the temperature of the water to reflect energy being lost from the reaction and being put into the solution, we have to know that whatever energy is gained by the water, which is the surroundings, must be the same as the energy that was lost in that reaction. And then, so when we sum them together, we get 0. And that's how we can do all of our calculations. So as I mentioned, I got a reaction going in a flask. The system is just what's in the flask, not even the flask itself. So whatever's in it. So that would be the reactants and the products. That's it. Even the things surrounding it inside, like the water or whatever, is not part of the system, because if it's not directly involved in the reaction, it is not part of the system. So it would be, the surroundings would be everything else outside of that. So what does that mean? So here's a new term I want to introduce you to called Q. Q is just what we use to quantify heat. So when you see Q, you know that you're talking about heat either going into a system or coming out of it. Now, two things you're probably very familiar with. Here I've got my cup of tea. So I got a cup of tea with hot water in it. Now over time, yum. Over time, my tea is going to get cold or come to room temperature. So it starts at high heat and then it goes down. And so heat is being released to the surroundings. Heat is being lost by the molecules in the hot water. So the water molecules are moving around quickly because they have a lot of kinetic energy. They lose that kinetic energy over time and start moving more slowly. The temperature goes down and that heat is then released. So we say that the change in energy is less than 0. It's been lost. So that would be a negative Q. It has lost energy to its surroundings. Now, on the other hand, if I had some ice water, so I've got some nice water in there, so the temperature of the system now is less than the surroundings. Well, what happens to ice water over time? The ice melts and the temperature goes up. So what's happened there? Well, the amount of heat in my system has gone up this time. That would be a positive Q, because now the molecules in the water are moving faster than they did before. All the ice is gone and the temperature has gone up. And so it has absorbed heat from the surroundings. The surroundings have actually put heat into the water. And so the surroundings have lost heat and the ice water has gained it. But remember, when I add them together, I get 0. My system has gained exactly the same amount of heat as the surroundings have lost. And so when you add them together, you get 0. So any questions about what Q is and how we can measure Q?
Yeah, just a general question, I guess.
Uh-huh.
Is Q only talking about surroundings, so not the system at all?
Oh, it's both. It's both. We can measure heat going into, so in other words, we can measure heat. If we're measuring, it's much easier to measure the system than it is the surroundings, right? We could like put a thermometer right into the water and measure the temperature of the system. So if the temperature goes up, as in with the ice water, that means that Q is positive, and Q of the system is positive. If the temperature goes down, that means Q of the system is negative. And one thing I want to point out, heat and temperature are not the same thing. Q is measured in heat, which is measured in joules. Temperature is measured in degrees. Man, I can't even remember, Fahrenheit or Celsius or Kelvin. That is different. So temperature is the measure of the average kinetic energy of the molecules in something. It is not the measure of the energy. We'll get into that a little bit later. All energy is measured in joules, and I will explain that in a minute. So that's Q. That's That's heat going from one place to another. What about work, though? Work is just W. That makes sense. So how do we define work? Well, here's a system on the left where its simple reaction is to take some zinc and to put it in some hydrochloric acid. And when you do that, it releases hydrogen gas. Now, it would just, if I didn't have any cover on my surroundings, on my system, it would just release hydrogen gas into the surroundings. What if I put a piston there with atmospheric pressure pushing up against it? Well, what would happen is that as gas was produced, it would push against that piston and push it out. It would actually do work. It would physically move that piston. It does physical work. And so that would be work done by the system. And strangely, we would say that that's negative. Why? Because energy has been lost by the system doing that work. And so it's negative. It has lost some amount of energy by doing work against the surroundings. Well, what if we do the opposite? What if I push that piston in? I do work on the system and push that piston in. So now the pressure inside the system is greater than it was before. That is, the surroundings have done work to the system. And now that would be positive, because the system now has higher energy than it did before, because energy has gone into the system in the form of work. So any questions about that? So if the system is pushing out, that's negative because work is being done to the surroundings and losing energy by the system. And then the opposite of that is pushing. And most of the work we're going to be talking about is called PV, delta PV work, change in volume or pressure. That's basically all of the work we're going to be talking about, is forcing the system to either change the pressure of something or change the volume of something. That's the work that's done in your car engine, for instance, when you burn either ethanol or octane or whatever fuel it is. It produces gases, CO2 and whatever other gases, that pushes the piston of the car, pushes it out, does work to the piston, and then turns the crankshaft and turns the wheels, and you turn that into physical work. So if the system is changing the pressure or the volume, that's negative work because it's doing work against the system. If we are pushing and increasing the pressure or decreasing the volume of the system, that is work we are doing, and it's positive to the system. So let's look at what so we need signs. Something's positive, something's negative. And remember, the change in energy is two things. It's either heat or work, or sometimes both at the same time. So what are the conventions? So positive means whatever our system is has increased heat. Generally, that means the temperature has gone up. If the temperature goes down and it loses heat, that would be negative for the system. Now for W, for work, just as I mentioned, if the system is doing the work, then that is negative. But if the surroundings are doing work on the system, that's positive. So if the energy of the system goes up because of work, it's positive. And if the energy of the system goes down because of work, it's negative. And so we have to add these two things together to find out whether or not the total change in energy is either positive or negative. We have to sum Q and W. Okay? So let's look at something you may or may not be familiar with. The first law of thermodynamics. which I sort of alluded to already. It basically says what I've mentioned before. The total energy of the universe stays the same. So any change in one thing, any change in any system is reflected in the opposite, equal and opposite change in the surroundings. So energy is conserved. You can't make energy, you can't destroy energy. All that happens is you're taking energy in one form and you're converting it to another. So when we do a reaction, we're taking chemical energy and we're converting it either to heat or work. That's all we're doing. Or we're doing the opposite. We're taking heat and work and converting it to chemical energy. It's equal and opposite. So when a plant absorbs solar energy and then into its chloroplasts, and then changes that into sugars that it can use later for energy, it's taking solar energy and converting it into chemical energy. When we eat sugar from sugar cane, we're then taking that chemical energy and converting it back into heat energy or work energy to move your muscles. You haven't created or destroyed anything. You've just changed the energy from one thing to another thing. So that's how we can basically do all these calculations, is by knowing that when you add one to another, you get zero. So if I measure one form of energy, I know what the other form is, because when I add them together, I get zero. That's how we do all of our calculations. So unit of energy, as I mentioned before, heat, temperature, not the same thing. Temperature we measure in degrees C or Kelvin, typically in chemistry, usually Kelvin. But with energy, there's a couple of different units you may be familiar with. You're probably familiar with the calorie, right? I mean, anyone who's ever been on a diet knows what a calorie is. A calorie that we actually know as a food energy is 1,000 calories, or a kilocalorie. Sometimes if you look at the label on food or whatever, it will actually say kcal, kilocalories, because that's what we think of a food. That's what a food calorie is. So if it says, so if you eat something that has 200 calories in it, it's actually 200,000 calories. Now, calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree. And that is the way we measure the heat from a lot of reactions. Basically, we do them in a container of water. So I would have water, then I'd have like a tube or something with my reaction going on in it. So here's my water. I measure the change in temperature of the water. Let's say the water goes up by 10 degrees C. Then I just convert that change in temperature by how much energy does it take to raise that amount of water by 10 degrees. Well, if there's 1,000 grams of water and it goes up by 1 degree C, that is 1,000 calories, or 1 kilocalorie. But the metric unit is the joule. And we have physicists to blame for this, because physicists refer to energy as basically accelerating the mass of 1 kilogram, 1 meter squared per second squared. It's their fault. Chemists were totally fine with the calorie because it made sense. Water we're interested in. 1 gram, that's metric. 1 degree C, that's metric. Everything was fine, but then physicists had to get involved and screw up the whole thing. So we're left with joules. And it's a simple conversion. So 1 calorie is equal to 4.184 joules. So the joule is smaller than a calorie. You don't have to remember this. If you have to do a conversion, I will give you the conversion. One other unit of measurement you may be familiar with is the BTU. refrigerators and ovens and microwaves and basically anything that bakes anything or involves a lot of heat is measured in BTUs. Like your refrigerator may have like be a 1,000 BTU fridge, meaning it can remove that amount of heat in a certain period of time. It's just basically it's a measure of how efficient it is at either removing heat or adding heat in the case of an oven. But we will be using joules from now on. Just to give you an idea of how much a calorie or a joule is. So this gives you an idea of like the massive amount of energy we get every day from the sun, just an insane amount of energy. So if we were to even be able to get like, let's say 5% of that energy, we wouldn't have to burn anything ever again. So it's an incredible amount of energy. You see that in one day, the energy that Hoover Dam can produce, which is about 1,000 times more than burning 1,000 tons of coal. So that's a lot of energy. Combustion of 1 mole of glucose is down there. So that, like a mole of glucose is about, see, it's at 180 grams. It's a lot of sugar. Shouldn't eat that much sugar, but there's a lot of energy in there. Excuse me. And again, that energy comes from the chemical bonds in the glucose. And we'll talk about how we get that energy out. So here's an yes, question.
Yeah. So you said 1 calorie needed to raise 1 gram, or is it is it 1 kcal?
1 calorie raises the temperature of 1 gram of water by 1 degree.
Okay.
Yeah. So if I had a liter of water, 1,000 grams, and I increased the temperature of that by 1 degree, that would be a kilocalorie. That'd be 1,000 calories.
Okay. Thank you.
So simple question here. So I'm burning gasoline in my car engine. The heat causes CO2, and because it's hot, H2O is now a gas because it's hot. That was a trick question in the last test. At room temperature, H2O is a liquid, not a gas. But in your car engine, it's a gas. Why? Because the temperature is really, really high. So you have 2 gases and some others, of course, expanding, pushing the pistons outward. Heat is something basically you don't want in your car engine. That's a byproduct. Because heat is basically you can't do anything with that energy. That's just lost. You would want all the chemical energy in the octane and whatever else that's in gasoline. You'd want that to be converted to work to push your car along. But most of it, I think about 70 to 80% of it, is lost as heat. So some work is being done by pushing the pistons. So the expanding gases do 451 joules of work. And the system releases 325 joules to the surroundings as heat. What would be the change in energy in joules, kilojoules, and kilocalories? So first you have to define what's the system, what's the surroundings. So the system is the reactants and the products of the reaction. The octane, the oxygen, the CO2, the water, the other gases being produced as products. And the surroundings are the pistons and the radiator and the rest of the car and the rest of the universe. So if we're going to be calculating, excuse me, Q, man, I'm having a hard time this morning. If we're going to be calculating Q, we're going to be calculating what's happening to the system. So heat is being released, so Q is negative, and work is being done by the system to the surroundings, so Work is -2. So let's have a quick look at what we would do here. So Q is negative because the temperature of the surroundings has gone up. So heat has been lost to the surroundings. Q is negative. Work has been done to the surroundings. Q is -2. So how would we define delta E? What would be the answer for delta E? Would I add these, subtract these, or some other form? What would be the answer for delta E? Change in energy of the system.
Is it Q plus W?
It is Q plus W. Always is. Yeah, so it's just Q plus W, so we just add them together. And so if we add them together, we get the two of them added together. Now that is in joules. Now it's a really quick conversion to change to kilojoules. We just multiply by 1/1,000. Now again, on a test, please do it this way because when you divide, you run into all kinds of problems. So this way, my joules go away and I'm left with kilojoules. Same thing for converting to calories. If I want calories, I'll put calories on the top. I'll put joules on the bottom. And then if I want to finish with kilocalories, I'll put kilocalories on the top and calories on the bottom. So calories go out, joules are left out, and the unit I have left is kilocalories. And they're all negative because Q is negative, W is also negative, and I always add Q and W together. Let's get into some of these. How do we deal with some of these? So here's two different things I can do with let's say a liter of gasoline. I can pour a liter of gasoline in a garbage can and set it on fire. I don't know why I would do that. Maybe I'm cold. So I just set it on fire. So basically no work is being done because it's open. There's no pressure, there's no volume change. I'm just burning it. So all of the energy from that, all the chemical energy in that octane is being released as heat, all of it. On the other hand, if I take that same liter of gas and put it in my car, it's going to be pushing the car along, doing work, and it's going to be warming up the car engine heat. But the same amount of energy is going to be involved in both. So this amount of energy as heat is going to be exactly the same as this amount. So Q over here will equal Q plus W over here. Same thing. Meaning all of these chemical and energy changes are path independent. Basically, I can add, it doesn't matter which way I get to from the chemical energy being released or the chemical energy being changed into heat and work. I can take a whole lot of different paths to get there, but I'll get to the same place at the end. So that is really important for what I'm going to introduce in a minute. It means if I can break down that reaction into a whole bunch of little steps, I can just add all those little steps together and get back and calculate how much energy would have been lost if I just did the whole thing at once. And that's going to be super important for doing some calculations.
Professor?
Yep.
Do you mind going back one slide before? On my slides, I can't do like the steps. Thank you. I just want to take a quick screenshot.
Oh, sure. That reminds me. Yeah, I'll also post the all the solutions here for chapters 7 and 8. I'll make sure I do that because the slides don't have the solutions in. I'll make sure I do that.
Okay, thank you.
Okay. So this will introduce us into something called enthalpy. I don't know if you may have heard this term before. Enthalpy is just basically a change in energy that where the change in energy is really most of the change in Q is really most of the change in energy. And that's true most of the time. Most of the chemical reactions we look at, there's very few that are like really doing work. Most of the time it's just changing the heat in the system. The most common work, as I mentioned, is changes in pressure and volume. And that only happens when the volume of the system changes or the pressure of the system changes, or you're pushing against an external pressure. So if we change work to change in pressure and volume, well, if the volume doesn't change that much and the pressure doesn't change that much, then W is pretty much zero. So most of the time, we can look at the change in energy as being the same as H, which is enthalpy. That's a new term. So enthalpy basically means energy change at constant pressure. And most of the time, most of the reactions we're going to be looking at, the pressure is not really going to change. And so the change in enthalpy will be pretty much the same as the change in energy. So most of the time we're going to be dealing with enthalpy, not so much energy, but it means the same thing 99% of the time. You just have to be aware of these circumstances. So these are the circumstances that we have to be aware of. So enthalpy, and again, that's delta H. Oops, go back. That's delta H. So if the pressure does not change, then that means that our work, P delta V, doesn't really change at all. And so enthalpy is going to be the same as energy. When is that the case? Well, if there's no gases involved, pressure can't change, right? If I don't take any gases out of the system or release any gases into the system, the pressure is not going to change. Okay. Well, what if the same number of moles of gases are taken out and then created again? If I have exactly the same number of moles of gases at the beginning of the reaction, at the end of the reaction, well, then the pressure didn't change then either. So, okay. So the total amount of gas doesn't change, no work either. What about if the change in Q is huge and the change in pressure or volume is really, really, really small? Well, then I can pretty much ignore P delta V under those conditions too. So then most of the time I am dealing with measuring enthalpy. And this is something that chemists talk about, enthalpy, because there's a whole lot of sort of advanced physics and everything else involving this that is different from heat when a lot of work is being done. Most of the time, a lot of work is being done. So we can measure this. So when I talk about energy pretty much from now on, delta H is what I'm going to be talking about. So let's look at some examples. Now we're being introduced to our old friends, endothermic and exothermic processes. Hopefully everyone sort of remembers what those were. So exothermic reaction is when heat is being released out into the surroundings from the system. So combustion reactions, classic example. Anytime you do a combustion reaction, heat is going to be released. And so you put your hands up against some sort of combustion reaction, they're going to get warm, right? Because that reaction is releasing thermal energy. It's taking the chemical energy in these bonds, So I've got H, these bonds are being broken and these bonds are being formed. So if you remember, if we go back to our redox, oxidation reduction, what is the oxidation number of carbon in methane and CH4? What would be our oxidation number for carbon under that circumstance? Anyone remember? What's the oxidation number of hydrogen? Pretty much all the time. Right, Nang. So if hydrogen is +1, what's the oxidation number of carbon?
-4.
Yeah, -4. So carbon at the beginning, its oxidation number is -4. What is it at the end when it's now in carbon dioxide? What's the oxidation number of carbon there?
It'd be +4 instead of
+4, exactly. So notice as carbon is oxidized, it goes from basically a reduced environment where its oxidation number is -4 to an oxidized environment where its oxidation number is now +4. And in doing so, energy is released. Thermal energy is released. And that's another thing that's really difficult for students to understand. Where do you think the energy comes from in this reaction? Is it from the carbon hydrogen bonds breaking in the methane, or is it from the carbon oxygen bonds being formed in the CO2? Where does the energy come from? Where's the release in energy come from?
I would think when you break something, it's releasing energy.
Okay. Anybody else?
Is the breaking of the bonds the exothermic process?
It's the opposite. The energy is actually released in the formation of the bonds in the carbon dioxide. And that's really hard to understand because you always think, well, I'm breaking bonds. I must be releasing the energy in those bonds, right? It's actually the opposite. You release energy when you make bonds. It takes energy to break bonds. You have to add energy to break those carbon hydrogen bonds. And that is the match that you strike, or the lighter, whatever you do, whatever spark you provide to start that reaction. What you're doing is you're breaking those initial carbon hydrogen bonds. That forms then carbon oxygen bonds, which are a lot more stable. And since they're a lot more stable, energy is released going from something that is less stable to something that is now more stable. And so it's actually the formation of bonds that releases energy. It's the formation of bonds that's exothermic and the breaking of bonds, which is endothermic. And we'll go into that a little bit later. But how do we deal with these different situations? So we're looking at enthalpy. So we're measuring enthalpy. And then we're looking to see which direction is the heat going. Well, heat is being released by the system. So as I go from a high energy state, I go to a lower energy state. As I mentioned, the bonds in carbon dioxide and water are more stable, are stronger bonds than these bonds here, methane and oxygen. those bonds are weaker than the bonds in CO2 and H2O. And so you take a little bit of energy to break them, and then you get a lot more energy released when you make the new ones. That energy is released. And so this system has lost energy. Delta H is less than 0. On the other hand, if I have ice, and then over time it turns into a liquid, heat has gone into the system. Liquid water is at a higher energy than ice. Why? Because those molecules are moving around faster than ice molecules do. They move around much, much more slowly, so much more slowly that is the solid. So heat has gone out from the surroundings into the system. So it's increased and enthalpy has gone up. So now the system has more energy than it did before. On the left, the system has less energy than it did before. Because once you've got carbon dioxide and water, there's not really a whole lot that can, not really a lot of energy there for you to take out of it. You can't burn it again. You can't really do much of anything with it. It is at a low state of energy. It's very, very stable. So we'll go through this together just because it's important to see how we take a chemical reaction and assign an enthalpy to it. So we need to determine the sign of delta H. Is it positive or negative? Is it an exothermic reaction or an endothermic reaction? So number one, how do we figure that out? So in each reaction, try and figure out, is the heat leaving the system or is the heat going into the system? If the heat is leaving, then it's a product. If the heat is going out, it's a product. And that would be that would be an exothermic reaction. If heat is going in, that's a reactant, right? It's going into the reaction and then going into the system. That would be an endothermic reaction. So look at number one. Is that an endothermic reaction or an exothermic reaction? What would we call that?
It'd be a melting reaction.
Number one.
Yeah.
So it's a melting reaction? That's not a physical reaction, that's a chemical reaction.
Oh, oops.
Basically, I'm burning hydrogen. That's a combustion reaction. That's when taking a hydrogen balloon and going boom. That's the Hindenburg reaction. So is that an exothermic reaction or an endothermic? Yeah, Farah says exothermic, right, because heat is a product. Heat's a product of that reaction. So I'm taking the chemical energy of hydrogen and oxygen and I'm converting it to heat, that much heat. So one of my products is liquid water and the other product is energy. Now, what about number two? I'm taking liquid water and converting it to water vapor. Is that an endothermic reaction or an exothermic reaction? Okay, I've got an exo. Anybody else? Got an exo, got an endo. Who's going to break the tie? Whole bunch of endo votes coming in. Yes, it's endothermic for a couple of reasons. One, heat is a reactant here. Energy is a reactant. So if energy is going into the system, that is an endothermic reaction. Energy is going into the system. So by definition, I'm adding energy to the system. That's endothermic. The other way we can look at it is just sort of, even if you didn't see the energy there, you look and see that the water at the beginning was a liquid. The water at the end is a gas. Energy is increased. It's gone from a low energy situation where the molecules are moving relatively slowly to a gas where the molecules are moving much, much, much faster. Energy must have been added for that to occur. So even without the energy there, we would know that that's an endothermic reaction, because at the end, the system has more energy than it did at the beginning. So for the first reaction, would we put a plus or a minus sign on the change in energy? Or 285.8 kilojoules. Would that be negative or positive?
Positive.
That's an exothermic reaction. So is it negative? Did the system lose that much energy, or did the system gain that much energy?
The system gained that much energy?
From the combustion reaction.
For number one.
Number one, okay. So if the system releases energy, does it mean that it has less energy than it did before, or more energy than it did before?
Less energy.
Less than. Yeah, so in an exothermic reaction, we say that's negative.
But
Now, what about the endothermic reaction, where energy's been put in, and now the system has more energy than it did before? That would be positive. Okay, so let's review, as they say. So for the first one, heat is a product. Heat came out. That is exothermic. So I went from a high energy situation where I had two gases, both moving around quickly, and then made a product that was a liquid. So in a lot of different ways, energy was lost. I went from high energy reactants to a low energy product. That system has lost energy. And so my delta H is negative, and I say it's exothermic. On the second, heat's a reactant this time. So it was on the left side of the reaction, right? So I had my heat plus liquid goes to gas. So the heat is going into the system, and it's changing my low energy reactant into a higher energy product. That takes energy to do that. Energy has to be added to the system to do that. So that is plus. At the end, the system had more energy than it did at the beginning. That is positive, and we call that endothermic. Okay, so what do we do with all this stuff? What's the point of all this stuff? The point of all this stuff is that, oh my God, stoichiometry again. Yes, stoichiometry again. Because we can treat energy as a reactant or a product. Well, if we can balance reactants and products, we can balance energy too. So a thermochemical equation, it's just another balanced reaction equation. We're used to balancing reaction equations. We balance the atoms on one side and the atoms on the other side. We balance the mass on one side and the mass on the other side. Well, now we're going to be balancing energy too. So the sign indicates whether energy goes in or energy comes out in the form of heat. And the magnitude of it is proportional to how much stuff there was. If I burn a liter of gasoline, or if I burn 10 liters of gasoline, well, when I burn 10 liters of gasoline, I'm going to release 10 times the amount of heat. It's proportional to the number of moles of product and reactant. So the value can be used, you can calculate it just the same way you would with moles. And in fact, that's how we define delta H with the reaction underneath is per mole. We always basically judge it per mole, because that way, if I measure the amount of heat, Q, released by burning 1 gram of hydrogen gas, and you calculate Q released when you burn 10 grams of hydrogen gas, we can both convert them to moles of hydrogen gas and get exactly the same delta H reaction, because it's per mole. So we just treat it the same way we would anything else. So if I have my amount of A, I have my amount of B, I make sure I get my molar, A plus 2B makes C. When I balance everything out, I also can balance the heat coming from this reaction, delta H reaction. Usually for every mole of A I convert, or every mole of C I make. Generally, you bring it down to per mole. So it would be joules, usually kilojoules, because there's a lot of molecules in a mole. So generally it's kilojoules per mole. Let's give you an example. So aluminum, we're all familiar with aluminum. One reason you find the production of aluminum is generally next to hydroelectric dams, and there's a reason for that. There's a reason for that because when you mine aluminum from the ground, the name of the ore, aluminum ore, is called bauxite. I don't know why it's called bauxite. You have to ask a geologist about that. But what it is basically aluminum oxide. Now, to form aluminum, you've got to get rid of the oxygen, right? Basically, you have to reduce the aluminum from its +3 state over here to its oxidation number of 0. You have to reduce the aluminum. Well, to reduce aluminum takes energy to do that, and it takes a lot of energy to do that. You can see to produce 2 moles of aluminum, you need 1,676 kilojoules of energy to do that. So the production of aluminum takes a tremendous amount of electrical energy, which is usually why I said there's a dam nearby or something that produces an insane amount of energy near an aluminum smelter, which is where you take bauxite and turn it into solid aluminum. So if you make aluminum this way, how many grams of aluminum can you make if 1,000 kilojoules of heat is transferred? Basically, heat is going into this reaction because it's positive. And another thing I want you to notice, you notice that there's a little delta sign over the arrow. That is a chemist's way of saying heat is involved in this reaction. You need to add heat to get it to work. So basically, if you heat aluminum oxide up to an extremely high temperature, the oxygen basically goes from being part of a solid to being released as a gas, and you're left with the aluminum. But it takes a ton of energy to do that. How would you calculate the amount of aluminum using that reaction? Well, you formulate a plan. So you look at the balanced reaction, and you see that when you put in 1,676 kilojoules of heat, you get 2 moles of aluminum out. That's part of the balanced reaction. That's a thermochemical reaction. Now, with that amount, you basically then take how much 1,000 kilojoules would be in moles. So basically all you're doing is you've got 1,676 kilojoules is related to 2 moles, as 1,000 kilojoules is related to X moles. And you just solve for the number of moles. Fairly straightforward. And then when you have your number of moles, convert that to grams. And if you can't convert moles to grams by now, we're in some serious, serious trouble. So here's my mass. I got my 1,000 kilograms. Convert that to moles. Take my moles, convert that to grams, and then I have my answer. Whoops. Then I've got my answer in grams. Can everyone see how that works? Basically, we're using the heat as another thing in the reaction. It's just another, just like the aluminum oxide, the other reactant is heat. The other reactant is energy. I need both of them to go forward and make the products. And so if I know what the molar relationship of the heat is to my reaction, I just use it like I would any other reactant and treat it exactly the same way. And that leads us to the whole point of this. And I'll sort of introduce this, and we'll go more into it this afternoon and on Friday. This is something called Hess's law. And boy, you're going to get excited about hearing this. So as I mentioned before, the path you go to for heat is completely independent. So if I think the example was if I take my octane and I just burn it and just release everything as heat, or if I burn it inside my car engine and release it as heat and work, I get exactly the same answer. So it doesn't matter which way I go. I can turn some of it into heat. I can turn some of it into work. It doesn't matter. I can break it down into any number of steps. And if I add all the steps together, I get exactly the same answer. Well, a clever German named Hess figured that out. And so if you wanted to calculate the heat involved in a reaction, and for some reason, and there's a lot of reactions, you can't really do that very well. If it's like a really hard reaction to do, or theoretically that reaction could take place, but you can't come up with a way to actually do it. What if you had a whole bunch of other reactions that if you added them all together, gave you that reaction that was really hard to do? Well, if you knew all the heats of reaction of all those individual reactions, if you added them all together, you would get the heat involved in your theoretical reaction. And chemists use this all the time to figure out how much heat would be lost in, let's say, a theoretical reaction, or if something's like really hard to measure, you can still measure it. So let me show you how you would do that. You can calculate the heat or the change in energy for an overall process, an overall reaction. Just get a series of reactions that when you add them all, add all the reactants, add all the products, cancel the things that are common on both sides. If you're left with the original reaction you're looking for, if you add up all the heats, you will also get delta H involved in that reaction. So let me show you some examples. These are some of the rules you'll need to do. Sometimes we need to flip a reaction around. For instance, if this was your reaction, makes water. Let's say one of my reactions takes up hydrogen rather than producing hydrogen. Or let's say it's a reaction producing hydrogen. Let's say it's zinc plus HCl makes hydrogen. Well, now I've got hydrogen. My initial reaction is hydrogen as a reactant. But this reaction has hydrogen as a product. But I don't want hydrogen as a product. I need it as a reactant. So what do? I just flip the reaction around and go backwards. But when I do that, I need to change the sign of delta H, because if it's an exothermic reaction going in this direction, that means it's an endothermic reaction going the opposite way. And the same thing. If it's an endothermic reaction going in this way, and it's plus delta H, well, then it's an exothermic reaction going the opposite way, and it's minus delta H. If I need, let's say I need 2 moles of hydrogen in my reaction, no problem. I just multiply everything by 2. But if I multiply everything by 2, I got to multiply my energy by 2 as well, because I've got twice as much reactants, twice as much product, twice as much energy involved. That makes sense too. So I can multiply by any number I want in order to satisfy what I need for my overall reaction. I can multiply and divide. I can switch them back and forth. But whenever I multiply, I need to multiply my energy by the exact same amount. Whenever I switch, I need to reverse the sign of the energy. And so at the end, everything except my target reaction, I got to cancel everything else out. So if I got water on one side, water on the other side, cancel those out. Just like in your redox reactions. If I have protons on one side and protons on the other side, they need to cancel each other out. So that all that's left is the reactants and the products in their target reaction that I'm looking for. Let me give you an example. It's kind of hard to explain this without looking at an example. So here's a reaction, fairly important reaction actually. I have carbon monoxide, I have nitrogen monoxide. Those are both really dangerous pollutants, much worse than CO2. And so one of the things in the catalytic converter of your car, that one of the reactions that it catalyzes is this one. So it takes a mole of carbon monoxide and a mole of nitrogen monoxide, puts them together and makes carbon dioxide, which, yeah, nasty, but not as bad, and nitrogen, which is, completely harmless. So when the environmental chemists were coming up with this method of doing it, they need to know how much reaction, what's the delta H for that reaction going to be? Because they need to design both the catalyst and they need to design, does this need to be cold? Does this need to be hot? What conditions am I going to need to do this reaction? I need to know whether or not it's going to be an exothermic reaction or an endothermic reaction. If it's an endothermic reaction, then it can be really hot. If it's an exothermic reaction, we might need to cool the system down a little bit. The reactions they did have that are well known is carbon monoxide plus half a mole of oxygen makes CO2. Okay, that's a fairly well-known reaction. That's an exothermic reaction and releases that much energy. It's also well known that if you take nitrogen and you combine it with oxygen, you get 2 moles of nitric oxide or nitrogen monoxide. That is an endothermic reaction. So they need to put those two things together and figure out, for this original reaction, is that going to be endothermic or exothermic, and by how much? Don't know. Well, this is where they use Hess's law to figure that out. So you look at the target equation, and the target equation is basically the target reaction, this one. Look and see where the reactants are and the products are. So carbon monoxide, that is a reactant, in equation A. Where is where is nitrogen oxide or nitrogen monoxide? Oh, that is a product in equation B. So I'm probably going to have to flip that one around. And I'm probably going to have to divide that or multiply that by 1/2 because I only need 1 mole. I don't want 2. So let's look and see how we would do that. So I take equation B I flip it around, and I multiply it by 1/2. So when I do that, I take the heat, oops, let me go back. When I do that, so before it was 2, 1, and 1. And the heat, if you remember, was plus. It was plus 180.6. Well, I've multiplied it by 1/2 and I've switched it around. So I changed the sign from positive to negative and I multiply it by 1/2. So now I have half the energy that I did before. But I have NO as a reactant, which is what I want. Then add the two things together. Oh, shh. Here's my equation A, my reactants and my products. Here's my equation B that I've changed, my reactants and my products. And I just add them together. So CO, that's only on one side, that stays. I've got 1/2 mole of oxygen as a product in equation A, and I got 1/2 mole of oxygen as a 1/2 mole of oxygen as a reactant in A. Here, let me change colors. I got 1/2 mole of oxygen as a reactant in A. I've also got 1/2 mole of oxygen as a product in B. That's what I would refer to as an intermediate. An intermediate is something that's produced during a reaction and then consumed. Produced and then consumed. It was like it was never there. So the amount of energy it took into creating and destroying it is exactly the same. So if I make it and then I destroy it, make it, destroy it, the amount of energy difference is 0. So I can just cross it out and it doesn't change the energy. So what else do I have left? I've got NO as a reactant, that stays a reactant. CO2 is a product, got my CO2 as a product. And the other product is 1/2 mole of nitrogen gas. That is my product. So I just add them all together. That's the amount of energy that was in equation A. I haven't changed that. But this is the new energy from equation B when it's flipped around and multiplied by 1/2. That goes here. And I just add them together. So you can see that this new reaction is even more exothermic than reaction A was originally. So it actually releases even more heat. So we just do one more quick one to give you an idea. How are people coping with all this? You see how we add reactions together. Take all the reactants, just like we do in the redox reactions. Take all the reactants, take all the products, and cross out the ones that are the same on both sides. Doing the same thing here. Does that seem fairly clear? Maybe another one will give you an idea.
Yeah, another one, please.
Sure. All right, so here is a reaction. Basically, what we have here is ethanol. I'm burning ethanol. So if I've got like if I'm burning a flaming shot of Sambuca or something, how much heat am I releasing when I do that? So first of all, we need a balanced reaction. Always need a balanced reaction. So 1 mole of ethanol plus 3 moles of oxygen release 2 moles of CO2 and 3 moles of water. I got 2 other reactions I can use to calculate that. So here is another reaction where I'm producing ethanol. I'm producing ethanol and oxygen. That, not surprisingly, is endothermic. And here's another one where I'm taking this reactant and I'm making that one. I'm making that out of carbon dioxide and water. And not surprisingly, that is also endothermic because I'm taking something with low energy. Carbon dioxide and water, as we've seen before, is low energy. If I need to basically reduce that carbon, back from like a +4 state to a -4 state, I need to add energy to do that. So a reduction reaction takes energy. Oxidation reaction generally releases them. So I need to add energy for that to happen. So both of these reactions are endothermic. Now, how am I going to take these two and end up with this? Well, let's see how we would do that. Let's clear all these. How do we do that? That doesn't make any sense. So again, this is the target we're looking for. What we want to do is find these two as reactants. If we find these two reactants on the reactant side, we're probably going to leave that equation alone, or multiply or divide it by whatever we need to get to 1 and 3. On the other side, we need to find carbon dioxide and water as products. So we need, if they're products of these other reactions, we probably leave that reaction alone and then multiply it or divide it to get to 2 and 3. So let's see what those other ones are. So the first reaction has our ethanol on the side of the reactant. So we leave that one alone. We keep it on the same side, but we only want 1 mole. Let me go back. We only want 1 mole of it. And so we divide that 1 by 2, because I only want 1 mole. So I take whatever that reaction was. If I flipped it, whatever I had to do to it to get ethanol on that side, and it appears, oh yeah, I did have to flip it around. It was endothermic before. So I had to reverse it and divide it by 2. That gives me this. So I did that to every reactant and product in the reaction. I had to reverse it, divide by 2. Every single thing I reverse, divide by 2, which means I also have to do the same thing to the heat. This was the original heat involved with it. I divide that by 2 and I switch the sign. Now with B, I just had to flip that around because that had carbon dioxide and water as reactants before. So I needed to flip that around and get them on the right side. So now, and CO2 had two CO2, so I don't have to do anything with that. I don't need to divide it or anything. I just need to switch CO2 to the right side. So the only thing I do with that one is change the sign. So now I've got 2 exothermic reactions. Now I just add them all together. So let's add them all together. So change colors again. So I've got 1 mole of ethanol. That's my 1 mole of ethanol. Now I've got oxygen. I got half a mole here, and I got 5/2 moles there. So I add them together for a total of 3. Okay, that's the right amount. So far, so good. Notice I have C2H4O liquid on this side, and I got C2H4O liquid as a reactant and a product on both sides of the arrow. So I can cross them out. I only have carbon dioxide as a product, okay? So that doesn't change. And again, I've got 1 mole of water as a product from the first reaction, 2 moles of water as a product from the other reaction. When I add them together, I get 3, which is what I want. 1, 3, 2, 3. 1, 3, 2, 3. So perfect. Now all I have to do is add the heats together. That's what I did to the first one. That's what I did to the second one. I add those 2 together, And that's my answer. So it should be exothermic because I'm burning something. I'm burning this ethanol and releasing CO2 and water as products. Well, we know that's a combustion reaction. That's going to be exothermic. So it's exothermic at the end. So you can see we took two endothermic reactions and used them to figure out that my original reaction was actually exothermic. So it's a little tricky to sort of explain. I think when you sit down with them and actually look, write them down on paper and start moving the things around, it'll make a little bit more sense. So we're gonna do some of these this afternoon, and we're going to do some on Friday as well. So I've for my two groups, I've posted a recitation under the recitation section in Canvas. Now, you won't be responsible for submitting it, but they are the problems we're going to be going over this afternoon. And for the other group, you can also download that, and I will post the answers for them as well. Okay?
Professor, how come
Yeah.
we reverse the sign for the first equation?
Oh, let me go back. So the first equation originally had ethanol as a product. So ethanol was a product in the first reaction. So we had to flip it so that ethanol was now a reactant. And there was 2 moles of it as a product, and I only want 1. So not only did I have to flip it, we also had to divide it by 2. So yeah, I have to admit, in that slide, it says that it wasn't reversed, but it actually was. So I will change that. I'll change that and then repost it, because they both had to be reversed. So yeah, that part was a little confusing. I apologize.
Also, is it normal for there to be fraction coefficients?
Yes, very much so. Because basically, when we're looking at these sort of reactions, when we're calculating delta H reaction, for this basically would be, what is the heat of reaction for burning 1 mole of ethanol? So for any 1 mole of that, basically, if it takes half moles of something to get to there, that's what you do. So that happens a lot, because a lot of times we'll be multiplying by 1/2 or multiplying by 3/2 or whatever to get to the proper coefficients. Because sometimes the coefficient will be 3 and for the product we want, and then the coefficient of one of the products or reactants will be like 5. Well, damn, what are we going to do? Well, we're going to multiply by 3/5 to get to the proper one. So yes, you're going to see weird coefficients in these sorts of reactions. But when you add them all up at the end, they need to come to the target. So whatever is in the target, you need to manipulate those other equations to get to that. So there'll be halves and thirds and all sorts of things.
Okay, thank you.
Yeah.
Professor?
Yeah.
So we should expect the sample questions or something like that to be on the final?
Yeah, there'll be one. Yeah, I will guarantee there'll be one Hess's Law question on there.
Okay.
I'll try not to make it too difficult,
Okay, thank you.
since we're just introducing it. But it's a really important concept. For those of you going on to 220, you're going to be doing this a lot. And for those of you that aren't, you're just going to hate me for this. So I'll just have to accept that. Okay, so I'll see most of you this afternoon. And then remember, so tomorrow is Wednesday. Yeah, office hours. So anything goes at office hours tomorrow. You have questions about the lab exam, questions about the final, anything. I'll be available at 11 till however long you need tomorrow. And then same thing next week. I'll still be having office hours on Monday and Wednesday. If a lot of people can't make it at 11, just email me and I'll I'll set up different times. Yeah, because I know you're going to have other exams next week, but yeah, I'm available. Yeah, actually Monday, Tuesday, and Wednesday next week. So just send me an email if you need to get together. Okay.
Thank you, Professor.
All right. I'll see you this afternoon, and also tomorrow and Thursday. All right. I'll talk to you soon.